Okay, so now we're going to go into how we actually conduct significance tests, and we're going to focus on population proportions in this section. And then we're also going to go more into like some of the concepts in how type 1 and type 2 errors tie into significance tests. And we're also going to look at confidence intervals and power. Okay, so similar to when we were constructing confidence intervals in the previous chapter, we have to check that conditions are met before we conduct the significance test. And these are actually pretty much the same as confidence intervals. We want to check the random condition, make sure the data come from a well-designed random sample or randomized experiment. The 10% condition, if we're sampling without replacement, check that we take no more than 10% of the population. And then the large counts condition. Both n times p naught and n times 1 minus p naught are at least 10. And then when we say p naught, it's basically what the null hypothesis value for proportion would be. That's what that little 0 or not represents, null hypothesis or HO. Make sure that they're both at least 10. Now, and again, I'll be talking more about this when we get deeper into it. But remember, these are like to make sure that we can use calculations based on normal distribution. That this is like kind of the formula, but this is basically to make sure that we can use the formula for standard deviation, that it's going to be accurate, and that this is approximately normal from the 10% condition. Now, the test statistic is basically the value that our data results in relation to the true proportion in this case. So it basically tells us how far the sample data is from the true mean. Well, not true mean, I guess, but I guess true proportion or the true average proportion, or depending on what we're dealing with. We're going to get to mean later. But this is going to be pretty similar, kind of the same as what you've been used to, because this is essentially what we started with in chapter 2, like the z-score. The z-score was a test statistic, and we're still going to use z-score here. But later on, we're going to see multiple tests. You're going to understand why we need this definition and this form, because it's not going to be always that simple to just assume, oh, it's going to be a z-score. But remember, it's talking about a value that allows you to compare relatively speaking, because we care about relatively speaking. And you'll see a good explanation of what I mean when we go through practice problems. But just building off that stuff in chapter 2, if you remember. Now, these will be like pretty much like the type of free response problems you'll get in your AP exam. So I advise, again, using this 4-step process, because it really allows you to hit all the necessary points so you can get full credit. And again, when graders are going over and scoring your exams, they like stuff to be easy. They don't want stuff to be all a mess. They want it to be smooth and, not for them not to work too hard. So the more organized and more formatted your answers are, more likely the better score you'll get. Anyways, we start with our state. We mention what hypotheses we want to test, our HO versus our HA, and what significance level. Like alpha is what? Like 0.05, 0.01, that sort of thing. And defining parameters, what our P represents in the context of the problem. In our plan, we identify our inference method. We haven't learned that many yet, but we're kind of just starting to probably catch on out there. This is important because we did confidence intervals in the previous chapter. Now we're doing significance tests. Later, we're going to do 2 sample significance tests, like difference of means and proportions, that sort of thing. And then check the conditions to make sure that it's okay to use. And the do is the fun part, where we do the calculations or the math. We calculate the z-statistic, or the z-score in this case, or the test statistic in general, and find the corresponding p-value. Then with this p-value, you make your conclusion based on what your alternative and null hypotheses were. And this, putting it together with our z-score, you want to decide, if you're going to be looking at, the probability of getting a test statistic that larger, or that smaller, smaller. So again, the test statistic, that we just went over in the previous page, in terms of population proportion, our sample statistic will be sample proportion, p hat. Our null hypothesis, or our parameter, would be p naught. This is just basically what we would assume to be true, like what the true population proportion would be. We use that naught to kind of help us identify that it's our null hypothesis value. And we're going to divide by the standard deviation based on assuming the null hypothesis is true. That's why our standard deviation is using p naught in its formula, not p hat. And then again, 3 ways to go about it depending on what the problem is. We have our alternative arguing that the true proportion is bigger than the null hypothesis claim. So if we're claiming that it's bigger, we're going to be looking at the area to the right of that z score, or that z statistic or test statistic. In the other case, case 2, we're saying it's smaller. So the area to the left of the z statistic or z score. And or not equal to, so both ends, to extreme, to the left and to the right. So again, this is just doubling, since we're using since it's a symmetric distribution, it's very easy to kind of find this once you know one side. The hard part in these problems is knowing what you need to identify, what you need to figure out. The calculation part is actually easy. So let's go through an example, because again, like always, I advise doing practice problems to get good at this stuff. All right, we're going to be going over a scenario dealing with American Idol. So in this TV show, contestants wonder if there's an advantage to performing last. If you remember, or maybe if you're not aware, American Idol is that the TV show has been on forever. It was on when I was a kid. It used to be good, but now there's like 100 of them, so I don't know what's going on. Anyways, the contestants are wondering, do I have a better chance of winning if I go last? So they did a study where they had a random sample of 600 college students and showed each of them the audition of 12 different singers. And to make sure there was no bias, each student saw the videos in a randomized order, which is, again, smart. It's a good study so far. Now, if there was no difference and there was no advantage in going last, then you would basically assume or expect that 1/12 of the students would prefer the last singer they picked, because again, it would just be an equal chance of picking anyone. Now, in the study, 59 out of the 600 actually picked the last singer they viewed. So 59 out of 600 is close to like 10%, which I know is more than 1/12. But is it that much more that we can say that we have some strong enough data to say that there actually is an advantage going last? So we're going to use an alpha level or significance level of 5%. And so if we get data that would occur less than 5% of the time based on just chance, again, based on assuming if this were true, then we would basically say, oh, we're suspicious and we have reasonable evidence to believe that there is an advantage going last, because this data only occurs less than 5% of the time. So let's go through it. So our state, mention your hypotheses, your null versus your alternative. Your null hypothesis, you're saying that the true proportion is 1/12. If there is an advantage to going last, the alternative is that P is more than 1/12. P is more than 1/12. Alternative hypothesis, or HO, is P is 1/12. P is 1/12 versus P is more than 1/12. using an alpha equals 0.05 significance level, and define the parameter. P is the true proportion of students who prefer the last singer they see. Our plan, if our conditions are met, we're going to perform a one sample z-test for P. So now let's check the random, 10% and large counts condition. Random, a random sample was used, and even the order was randomized. So that's good. That condition is definitely met. 10%. Remember, we're talking about the sample size. I want to say that 600 is no more than 10% of the population. So we basically want to say that we can reasonably believe that the population is at least 6,000, and that makes sense. There's at least 6,000 students in that population. And large counts. Remember, it's going to be n times p naught. It's often confused as n times p hat, but remember, we're assuming the p naught to be true. So 600 times 1/12, and then 600 times 1 minus 1/12. Since this is 50, we know the other one has to be 550 because they have to add up to 600. Another way to think of this is number of successes and number of failures. They're both at least 10. So all conditions are met, so we can go to our do part. So this is the fun part. We do our calculation. We use our z statistic to calculate some value where, we use basically our formula. This shouldn't be the hard part. This should be just algebra. Our p hat, first make sure we know what we're doing there. That's the new value here. Our p hat is a 59 over the 600. So here's our formula in general. Just to review it. P hat 59 over 600. P naught, the 1/12. P naught 1/12. 1 minus 1/12, 11/12, and the 600. As long as you do this all correct, rounded approximately would be about 1.33. Okay, so now make sure you know exactly what you're looking for conceptually speaking. This is our z statistic. We're trying to find what the chance of getting a z statistic of this value or more would be by chance, because we're saying that the alternative is p is more than 1/12. So let's turn the page and let's actually draw a little picture so it makes sense. So we want to find this area here. Like, what would this p-value be? And this is standardized already. This is the standardized, it's their z-score essentially, just for this, first type of significance test. That means the mean is 0, standard deviation is 1. So we can just basically use technology, normal CDF. Our lower bound would be 1.33. Our upper bound, just make it like infinity or billion, whatever. Our mean, 0. And our standard deviation, be 1. So let's see what we get when we do that in our calculator. So go into distribution. Distribution, normal CDF, 1.33, lower bound, comma, upper bound, mean of 0, standard deviation of 1. And again, if you have a more advanced calculator, a newer version, it probably is really easy to know where to plug in the right numbers. This probably has like columns or rows. In either case, you get about 0.091. So 0.091759. So this is our p-value. So that's our p-value. So what do we conclude? We get a p-value of about 9% but our alpha level is 5%. So it's basically saying that the chance of getting data this extreme or more based on if we assume that the null hypothesis was, if we assume the null hypothesis was true, we would have about 9% chance of getting data this extreme or more. And that's not a big deal, and that doesn't exceed our alpha level, which we set ahead of time. So we're going to fail to reject HO. So because our p-value about 0.0918, whoops. It's greater than our alpha equals 0.05. We reject HO. Oh no, we failed to reject. We failed to reject HO. We failed to reject HO. And let's think what that means in context. We failed to reject HO. It's basically saying that we don't really have convincing evidence to say that there is an advantage of going last. That there is an advantage to performing last. All right. So there we go. There's an example of how we go through a significance test for population proportion. So I hope that helps, and good luck.